Hello everyone, welcome to this presentation on unsteady heat transfer. Today, we'll be walking through an example problem to understand how to analyze the transient cooling of an object. Specifically, we'll be looking at an aluminium alloy plate that is suddenly quenched into liquid oxygen. This scenario is a classic example of unsteady heat flow, where the temperature of an object changes significantly over time. Here's the problem we'll tackle. An aluminium alloy plate measuring 400 millimeters by 400 millimeters by 4 millimeters is initially at a temperature of 200 degrees Celsius. It is then abruptly immersed into liquid oxygen, which is at a frigid minus 183 degrees Celsius. Our goal is to determine the exact time it takes for this plate to cool down to a temperature of minus 70 degrees Celsius. To solve this problem, we'll use the following given properties for heat transfer coefficient, specific heat capacity, and density. Now let's dive into the solution. The first step in solving any heat transfer problem is to identify and calculate the relevant geometric properties. For aluminium plate, we need its surface area and volume. The surface area AS is calculated as 2 times the area of one face, giving us 0.32 meter squared. The volume is simply the product of its dimensions, resulting in 0.000064 meter cubed. Next, we calculate the characteristic length LC, which is a crucial parameter in unsteady heat transfer. It's defined as the ratio of the volume to the surface area. In our case, LC comes out to be 0.002 meters. This length helps us to determine if the lumped capacitance method is applicable. To proceed, we need to determine the thermoconductivity K, which is given, and we use the value that is in the slide, and we can now calculate the Biot number, BI. Now the Biot number is a dimensionless number that tells us the ratio of conductive resistance within the object to the convective resistance at its surface. So it's calculated as HLC divided by K. So plugging in our values, we get a Biot number of approximately 0.0519. Since our calculated Biot number is 0.0519, is significantly less than 0.1, we can confidently apply the lumped capacitance method to solve this problem. This method simplifies the analysis by assuming a uniform temperature distribution throughout the object at any given time, which is a valid assumption when the internal thermal resistance is much smaller than the external convective resistance. The lumped capacitance method confirmed, we can now use the governing equation for temperature distribution in unsteady heat transfer. This equation, shown here, relates the temperature at any given time to the initial and ambient temperatures and a time constant. The formula is as presented. Now let's substitute our known values into this equation. On the right side, we plug in the heat transfer coefficient, surface area, density, volume, and specific heat. This gives us the expression you see on the screen. After performing the arithmetic, the left side of the equation simplifies to approximately 0.295. The exponential term on the right-hand side becomes exponential minus 4166.67 tau. We can then rearrange this equation to isolate the exponential term, which is equal to 1 divided by 0.2 0.95 or approximately 3.389. Now to solve for tau, which represents the time, we take the natural logarithm on both sides. This allows us to bring the exponent down. Finally, after a few more calculations and converting the time from hours to seconds, we arrive at our answer. The time required for the plate to reach -70 degrees Celsius is approximately 1.054 seconds, and that is our final answer. Thanks for watching. If you found this video helpful, please consider subscribing to our channel for more content like this. Don't forget to hit the notification bell so you don't miss out on our latest uploads.